Okay, so a beam supports three loads as shown. The material used for the beam has a normal stress. So sigma max is 1800 psi and shear stress of 120 psi. Determine the minimum depth D. Depth D is shown here, such that it meets strength constraints specified by the given stresses. Okay, remember that sigma is m y divided by I. That's how we compute the normal stress. And tau was PQ divided by IB. So what we'll do is let's try to write these formulas in for the specific beam, which has a rectangular cross section. So when there's a rectangular cross section with B as the width and D as the height, you can write sigma is m D divided by 2 B D cube divided by 12. And remember that the maximum stresses will occur at the outer and inner edges. So sigma max is here and sigma min is here. It just depends on how m is. If m is compressive, so m is clockwise, anti-clockwise, we'll have this thing exhibit, but the maximum and minimum are the same magnitude, but opposite sign. So we can simplify. This is actually, let's write it as sigma max. Or rather, let's just keep it at sigma. Sigma equals m for 12 m, or the 6, right? So you can cancel off the 12 with 6, common factor is 6, p d squared. Okay, so that's the formula for the stress, normal stress. Okay, let's do the same thing for shear stress. Yeah, is it wrong? 6. I'm sorry, my sigmas look more like my 6. Maybe it's bigger. Okay, so we can also do the same thing for tau. However, there's a table which we can refer to and don't have to do all the calculations for tau. So if you remember, I'd drawn this table. I put this table in the notes. So we are looking at the rectangular cross section, and then you're already given that the tau max occurs at neutral axis. The value is 3V divided by 2A, where A is the cross section area So we just use that from that table instead of deriving it. But can we derive from the formula? The table tau equals 3 divided by 2 p divided by a. So area is b times d. That's the cross-sectional area. So that's our formula for tau. Okay, something to remember is that this stress is maximum at the neutral axis. That's our beam. Tau max. Okay, so I wrote these formulas down so that we can now sort of see how to go about solving the problem. We have been given the maximum normal stress sigma. We've been given the maximum shear stress tau. We know from beam theory that the maximum stress is that formula, sigma equals 6m divided by bd square. And the maximum stress occurs at the outer edges. Okay, so if you can put sigma max and if you can put the maximum moment on this beam, then you can compute d. Okay. You can also, if you're given the maximum shear stress tau on the right side, and if you can find the maximum b on this particular beam, then you can again compute d using that. So what needs to be done is we need to do our design calculations, assuming the first criterion that it fails in normal stress because of the normal stresses, compute a d and see if it meets the requirement for shear stress. Okay, if it meets the requirement for shear stress, a design is good. The other way to go about designing this is to first use the maximum shear stress as the design criteria for D, and then checking sigma if it meets the sigma maximum limit. So this is one of those problems where they're given two things, but you don't know which of those two applies towards for this problem. So the D will be based on whichever meets the criterion that both those conditions are met. So before we even go ahead and solve for D, D, we need to find what M and B is, right? Without M and B, we cannot solve it. So our first goal would be to find the shear force as a function of distance, find the bending moment M as a function of distance, identify the places where M is max and B is max, and then use that in these equations. Okay, so we'll do that first, and then come back, revisit these formulas. So put that down. So first we'll compute Bx and Mx. Okay. Okay, then as I said, you could start off with one of those two criterions. So let's say we'll use sigma max to design for D and check if tau is less than tau max. If that's not true, then use tau max to design for D and check if sigma is less than sigma max. Okay. So if the second step checks out, we don't have to do this step number 3. And vice versa, right? So if 2 checks, if two so if this is true, then this is use this T. If it's untrue, then you go to the step true and then check this. If this is true, then use this T. This step only if 2 is untrue. So I think it will become clear once we go about solving this, and you can go back and go to this. Two is not true, right? So here, if you make a good guess that you start off with 3, for example, then it works out that you don't have to do 2. Okay, you have to choose one of the 2, so you can go either way. Okay, so let's first do step number 1, compute the shear force and bending moment diagram. For that, I need to draw the free body diagram. Now, this beam looks kind of weird, right? I mean, these supports are not known. We don't know what the supports are at A and B. We're just going to make an assumption that those supports are roller on one side and hinge joint on the other one. And that is okay. If you're not given support, you can assume that. You could also assume it's like a fixed support. But I think if you do a fixed support, you'll see that you'll end up with more unknowns than equations, and then you'll have to use something which we have not done here on how to compute those moments which will appear at A and B if you assume it to be a fixed support. So we'll just assume it to be a simply supported beam, and that will make our life easy. Yeah, that's right. So you can to give you 3 questions, 3 unknowns. We have only 3 questions, right? Fx, Fy, and M. You need to assume a pin joint on one and a roller joint on the other one. That way you'll get 3 unknowns. The pin would have two unknowns, and the roller would have 1. If you assume pin and pin, then you will end up with two for the pin to this side, to other side, you'll end up with 4. And there'll be some ambiguity on the forces. In this case, the horizontal forces don't really matter. So you could assume that too, and it won't really change anything. So pin is fine, pin hinges, pin roller is also fine. So you can arbitrarily decide which of them you want to be a pin joint. So in this case, I put a pin joint on the left side, but you could do on the right side. You could also, if you want, put a pin joint like this. So if you do that, then you will not be able to find HA or HB. You'll only be able to find the sum of them, which is equal to 0. Or in this case, HA minus HB is 0, but that really doesn't affect our solution. So let me remove that just to make it less confusing. Well, it's like this is a system which looks like it's built out of wood, right? And then the thing is, you want to make assumptions. And when you make an assumption like the one I assume, you want to check if the assumption is true in the real system. Just to make it tractable, in this case, I assumed it to be what I assumed it to be, which is pin and roller. But yeah, you would want to possibly do it with other kind of supports and see if that's a better assumption for your system. Okay, so the lengths are 2, 3, 3, 2. looks like will come out to be something symmetric. So VA plus VB equals, what's VA plus VB minus 2.5 minus 1 minus 2.5 equals 0. And this gives us VA plus VB equals 6. And then if you take moments about A, okay, what do we have? We have 2.5 acting at a distance of 2, and 2.5 produces, this is the one which is closer to A, produces a clockwise moment about A, so negative. 1 is at a distance of 5 from the left and would produce a clockwise moment, so negative. And then 2.5, the one which is closer to B, is at a distance of 3, 6, 8, and also produce a clockwise moment. And then VB is at a distance of, I think, 10 from A, and it would produce a counterclockwise moment. So all this is equal to 0. So this enables me to solve for VB. Comes out with 3. And so VA is also 3, 6 minus 3, which is 3. And this is Gibbs.
So the first question we solved, we said this is symmetric, so we just did it. So in the same question, can we do it the same way too?
Yeah, so the simpler way to do it is to write that equation VA plus VB, and then say VA should be equal to VB because this is symmetric. And then answer is VA equals VB equals 3. That's perfectly fine. But you need to be careful that it should be symmetric, not only. So here it's 10 meters, but exactly there's 2.5 on the left, 2.5 on the right at the same distance from A and B. And so it's symmetric. So the moment I change that 2.5, one of those 2.5 to 3.5, you cannot do that assumption. But this is, you don't need to do the moment equation. You can just do it from step. So absolutely, if you write symmetric, VA should be VB, full points, no problem. I don't recommend this to people because then they may incorrectly assume things and get the wrong answer. It's always safe to do this way.
It's just the first question we saw that saying symmetry, that's why.
Okay. There was another one, I think the first one, right? The previous, yeah, that one was. Yeah, but you could do the same and check. Okay, so we've got the shear forces. Let's draw the shear force diagram and bending moment diagram. And that's actually kind of simple for this one, as you'll see. So 3, 3. And the lengths are 2, 3, 3, 2, or rather 2, 3, 3, 2. Let's draw the shear force diagram. Okay, we have a force of 3 upwards, so would be 3 is here. Okay, then it will remain constant till we hit the 2.5. So it'll be 3 upwards, 2.5 downwards. So 3 minus 2.5 is 0.5. So negative 0.5. No, that's not right. 3 minus 2.5 is 0.5. Okay, so we keep going. When we reach the middle, we have 1 downwards. So we should subtract 1 from 0.5. So we have minus 0.5. It remains minus 0.5 till we hit 2.5. That's downward again. So that gets added with a negative sense to negative 0.5 to give us minus 3. Then keeps going, and then once we reach the right side B, we would get 3 minus 3 plus 3, 0. Okay, now drawing the bending moment diagram is easier if we use the area method. Okay, so let's compute the areas, which are area under the curve for each of those blocks. So we have 3 on the y-axis, and this is 2, this is 3, 3, 2, and that's the, it's right in a different color. So 3, 2, 3, 2. So the area is going to be 3 height and 3, oh, sorry. Be 3, 2. Okay, so this area is 3 times 2, which is 6. This area is, height is 0.5, length is 3, so 3 times 0.5, 1.5. This area is minus 1.5, the same as the previous, but with the negative sign. And this one is going to be 3 times 2, minus 3 times 2, so it's going to be minus 6. Okay, let's draw the bending moment diagram now. So on the left side, which is A, there's no moment there, so we should start at 0. Then going from A to this point where there's a 2.5 Kipps force near A, the moment is 3 times 2, 6. So I need to go all the way to 6. Okay, so how do I join those 2 points? Well, if the shear force V is constant, the integral of a constant is a straight line, right? And a straight line should pass from 0 to 6. So then we have the area is 1.5. So the next point is going to be 1.5, which needs to be added to the previous moment. So 1.5 plus 6 is 7.5. Again, it's a straight line, same reasoning, constant integral of constant is a straight line. Okay, then we have a negative 1.5. So I need to subtract 1.5 from 7.5. That's 6. And then I need to subtract minus 6 from 6. So I end up with 0, which agrees with the moment at B. The moment at B is 0. So remember the formulas. Sigma was 6m divided by BD squared, and tau was B divided by, or 3V divided by 2 PET. Okay, so we have both those diagrams, and that will be helpful for us when we solve for D. Okay, so that's step one, which is getting those diagrams. Now let's go to step two. Okay, use sigma max to design for D and check if tau is less than tau max. That's what we're going to do next. So step two, use sigma max for design and check tau is less than tau max. Okay, so if you put sigma max in the formula, we have sigma max equals 6m max divided by PD square. So sigma max is given to us. That's the maximum stress which is dependent on the material, and it's given to be 1800 psi. Okay, now this equals 6m. Now, m is, you need to be careful about the units. This is psi. The b is given to be in feet. Okay, so I need to convert feet. So that's 3 point. Okay, it's given is given in inches. So we're good because psi is an inches measure of inches, right? The I denotes square inches, so it's pound square inches. So we're good on there. So 3.5 is B. D is unknown, and then we need to write the value for the moment in terms. We need to find the maximum moment and write it in the units of inches. So or IPS. So M is, let's see, 7.5 is the maximum. What's the unit for this? So remember that this is kips. The feet, kip feet. There will be kip feet. Because this was in kips, and then we multiply this with feet, right? All these dimensions were in feet. That's why we have kip feet. And so what we need to do here is, in order to put it here, we know that 7.5 is the maximum, but we need to convert that to inches. So it's 7.5 kip feet, which will be 7.5 times 10 raised to 3. That's to convert the kip to remove the kip, the kilo in the kip. And then since all these inches, all these dimensions are in inches, that is B is in inches and D is in inches, we need to convert feet to inches. And you know that 1 foot is 12 inches. Okay, so this is what goes in here. So 1800 equals 6 times 7.5 times 10 raised to 3 times 12 divided by 3.5 D squared. So solve for D. 6 times 7.5, 10 cube times 12 divided by 1800 times 3.5. And I took the square root of all this. And the answer is going to be in inches. So I took care of that in the way I set up M. So we're 9.258 inches. Okay, so once we do this, let's check if tau is less than tau max. Okay, so now we've completed the design, we know the design D, and now we want to check what's the maximum possible shear stress based on the calculation we did, which is D equals 9.258. Okay, so we need to use this formula where D is given to us. We already solved for D, but we need to find the place where V is maximum. Okay? So V is maximum at, well, it's maximum here as well as here. Okay, remember that the maximum normal stress occurs here, but the maximum shear stress occurs anywhere here or here. So the locations where the maximum shear stress is different from the place where the maximum normal stress occurs. Okay, that's kind of important. So we'll use 3 for this, but 3 should be, well, it's basically kips. So I need to multiply by 1000 to convert it into IPS. So let's check the design. Tau equals 3 by 2 V divided by B times D, which is 3 by 2. 3 divided by 2, V is 3000. B is 3.5 inch, and D is now known 9.258. Doing this math gives me 138.8 PSI. Okay, now tau max happens to be 120. We can look at the question. It says the maximum stress is maximum shear stress you can bear is 120, which means clearly that if we design it based on M or use 9.258, then it's going to fail in shear at a different point, not the same point, where it would potentially fail with normal stress. So tau is greater than tau max. So the beam would fail. In shear. Okay, so we need to go back and redesign this using the shear stress and then check for the normal stress. So last step, number 3, design based on tau max and check sigma is less than sigma max. So tau max equals 3 by 2 V divided by BD. We've already seen that the maximum stress occurs, maximum shear force is at the points I showed you, those 3000. B is 3.5. D is unknown, and the maximum shear stress is 120. So I can use this to solve for D. So 3 divided by 2, 3000 divided by 120. And this gives me 10.714 inches. Okay, that's the design. Check sigma is less than sigma max. For that, I write the formula for sigma. it's 6m divided by bd square. When I use the m, I need to use the maximum m. So we remember it was 7.5 occurring right at the middle. And so 7.5 times 1000 times 12 to convert into IPS. B is 3.5, D is 10.714 square. That's comes out to be 1344071 PSI. Sigma, or which is 1344.07 on PSI is less than, so the maximum normal stress allowed by this beam is 1800, which is sigma max. So sigma is less than sigma max. So design is acceptable. So the answer is D is 10.714. Is the final. Now, we could have saved a lot of time if we had started with this assumption. And then we didn't have to do the other check.